Hey guys, welcome to section 10.3 polar coordinates. We are so close, this section, one more section, and we will be good for the semester. This is kind of a cool section if you enjoyed the previous section. It's different but similar in the sense we're looking at things in an XY plane a little bit differently. Polar coordinates uses angles and distances to look at points in a plane. So let's take a look. What we start with is we have our XY axis, and we call the origin, we call it the pole or the origin. So when we're looking at polar coordinates, they tend to call the origin the pole. So that's just where the X and the Y axis meet. We call the positive X axis the polar axis. So if we have some point in our XY plane, we're now going to call this point, instead of going over X and up Y, we're going to identify it a different way. We're going to identify it with an R and a theta. And what R is going to be is the distance the point is from the pole. So this distance is going to be R. And theta is going to be the angle that starts at the polar axis and goes to the line that connects the point to the pole. So this would be theta. So the point is still just that point right there. So now here, this is a demonstration for when R is positive. R can be negative. What happens when R is negative? We still are going to, so like if we have a negative value of R, we're still going to use this angle right here from the pole to the point. But if we were to have a negative R, what we would do is we would first identify R in theta. So this would still be R right here. So if this was my point R theta, let me see, R is positive here. Bear with me for a second. I don't think I said that quite right. So that's the distance R. This is still the angle theta. But if we take the opposite of R, it would still be this angle. What we would do is travel down that line in the opposite direction of the pole right here. So we would take this distance. We would go right here. This point right here. The coordinates of this point would be negative R theta. So we would travel up theta, an angle of theta. We would go distance R away from the origin, and that would be R theta. Negative R theta would be in the opposite direction. So the length here is still R. R technically is always positive. So if there's a negative in front of it, it's just switching the direction. All right, so I don't know if I said that too well, but let's look at a couple of examples and see if I can clarify, redeem myself a little bit here. All right, let's plot each point. Plot point A, B, and C. So 3 separate points. These get a little tricky because we have to, 45 degrees isn't too bad. 135 is not bad, but it gets a little bit trickier when we have angles that aren't so obvious. So 45 degrees, all right, what I have here, I'm not sure if you can see it, but I've drawn lightly concentric circles, each of, I think they were 1/2 of an inch, so they're going to each represent 1 unit away from the origin. So if I wanted to identify the point 45, well, 45 degrees is clearly, it cuts, 45 degrees cuts the X in the first quadrant right in half. So I'm going to say about right there. Whoops, sorry. So it cuts it. It's the diagonal line Y equals X. So this would be 45 degrees, right? So 45 degrees would be there. So this would be my angle, 45 degrees. And then I had every 1/2 inch represent a unit. So if I go up, 4 would be 2 units up. So I'm going to go 1, 2, 3, 4. So there would be my point right here. So like that's kind of like we're looking at it that way. So I went up 4 units. And there's actually cool graph paper. So if you Google polar coordinate graph paper, instead of being blocks, it'll give you graph paper with circles. And it makes it a lot easier to plot these things. So this angle right here is 45 degrees. Right, I went up 4 units from the center. So this point right here would be the point for 45 degrees in polar coordinates. So that's point A. Point B says go 135 degrees and then go -5 away from the origin. So 135 degrees, well, 135 degrees cuts, it falls on the diagonal line, Y equals -X right here. Right there. So there's, this is my angle, 135 degrees right here. Is 135 degrees. So if I went up, I said every 1/2 inch right here, represented a unit. So if I went up 5, I'd be at 1, 2, 3, 4, 5. I would be right here. So this would be the point, and I'm going to write it down, but this would be the point 5, 135 degrees. But that's not the point we're looking for. We're looking for -5, 135 degrees. So I go 135 degrees, and I'm going to be falling on this line, but instead of going up 5, I'm going to go down 5. I'm not going to fall on the terminal side of the angle 135 degrees. So that being said, if R is positive, your point will fall on the terminal side of this angle. If R is not positive, you draw this angle and you go onto the opposite side of the terminal side. So I'm going to go 5 units down this way, right there, and this is the point, right? This would be the point, -5, 135 degrees. So that would be point B. Now, what's kind of interesting with polar coordinates as opposed to Cartesian coordinates is Cartesian coordinates have one representation. If we go over 2 and up 2, it's like if we went left 2 and up 2, that would be the point -2, 2, and that would be the only option. This point, notice, I can go 135 degrees, and then I can go down 5 units, or I could have gone this way. That's -45 degrees. So this point also could be written -45 degrees could be my angle, but this time, -45 degrees, this would be the terminal side of -45 degrees, and the point falls on the terminal side. So I could call that point 5, -45. So the point 5, -5, 135 degrees, and the point 5, -45 degrees represent the same point in the XY plane in polar coordinates. So as you can imagine, there's infinitely many ways we can represent a point in Cartesian coordinates. In polar coordinates. In Cartesian coordinates, there's only a unique way. All right, lastly, we're going to go 2 pi over 3. My brain works better in degrees. So pi over 3 is 60 degrees. So this would be 120 degrees, right? So we're going to go 2 pi, 120 degrees is just shy. And if you get that, look up that really cool paper, and if my printer was working, I would have printed it off. But 120 degrees is just shy of 135 degrees right here. So I'm going to pretend this is pretty close to 120 degrees, and I'm going to draw this angle right here. So if that's 120 degrees, right from here to here, 120 degrees, and then I'm going to go up 2 units. That would be the point, up 2 units. So here would be my point C. That would be the point 2 pi over 3, right there, right? And that's, my friends, how we plot points in polar coordinates. Now, there's not any examples like this, which is upsetting to me in XYZ, but please make sure you're doing your work in your textbook, and you will find problems like this in your textbook. So, yeah, definitely do that, okay? All right, connection between polar and Cartesian coordinates. Ready? All right, so if we're given a point, let's just say we have this point right here, XY. Okay, if we imagine this in our polar world, let's just draw our triangle right here. This would be, if we looked at the length of this line right here, would be R. And if we drop a line, if you remember from your trig days, we always drop vertical lines to the x-axis. We never go to the y-axis. That provides us with misleading information. So we draw this, we look at this right triangle. If you agree, the side of this triangle is x, and the side of this triangle is y. So now I'm drawing it in the first quadrant, but this works for any point in any quadrant. So the angle from the x-axis to the line that connects the point to the origin is the angle in our polar coordinate. So this would be equivalent to the point R theta as drawn, okay? Now notice if we use our trig, isn't it true that the cosine of theta, and if we look at this triangle using right triangle trigonometry, well, the cosine is the adjacent over the hypotenuse. So it would be x over r, or equivalently, x is r cosine theta. We can also say that the sine of theta is the opposite over the hypotenuse, y over r, so y is equal to r sine theta. Also notice, it's a right triangle, so isn't it true that x squared plus y squared equals r squared? lastly, we can look at this relation. The tangent of theta is equal to opposite over adjacent, y over x, right? So like I said, this figure shows r being positive. It also shows our angle being between 0 and pi over 2. These equations are valid for all values of r and theta. All right, converting from polar to rectangular coordinates. If you're given a polar coordinate and you want to put it in rectangular coordinates, keep in mind we're given the polar coordinate r theta, x is equal to r cosine theta, and y is equal to r sine theta, as we just saw with the diagram on our previous page, right? So let's convert the polar coordinates 12, 5 pi over 3 to rectangular form. So x would equal 12, because this is r, and this is theta, so it'd be 12 cosine of 5 pi over 3, which is 12, well, the cosine of 5 pi over 3, well, it's a multiple of 60 degrees, so it's a half. It falls in, keep in mind, all right, if we go 5 pi over 3, we're going to be in quadrant 4. Keep this in mind, this is really super important. To make sure when you get your x and y coordinates that they also fall in quadrant 4. 5 pi over 3, well, pi over 3 is 60 degrees, times 5 is 300 degrees, so we know we are in the 4th quadrant. So it's going to be 12 times 1/2, which is 6, and y is equal to 12 sine of 5 pi over 3. And so that's 12. Well, 5 pi over 3 is 300 degrees. It's in the 3rd quadrant. The sign is negative. It's going to be square root of 3 over 2. So it's going to be negative 6 square root of 3. So therefore, the xy equivalent would be negative 6 square root of 3. Now we would just have to pull our calculator, get an approximation of what negative 6 square root of 3 looks like in order to plot this, but I'm sure you can do that. All right, let's try one more. Convert 6 240 degrees to rectangular form. So r is 6, 240 degrees is theta, 240 degrees is in quadrant 3. So keep that in mind. Our x and y values should both be negative. So x is going to be 6 cosine 240 degrees, which is 6 times cosine of 240 degrees. Well, again, it's a multiple of 60, so it's 1/2, and it's in the 3rd quadrant, so it's negative, so negative 3. And then y is equal to 6 sine of 240 degrees. So the y value would be 6 negative square root of 3 over 2, which would be negative 3 square root of 3. So both the x and y coordinate are negative as expected because we are in quadrant 3. So xy is going to be negative 3 square root of 3. So pretty simple if you're comfortable with your trig. If you're asked to convert and your angle is not one of the basic angles that is a multiple of 30 or 45, then these may not come out to be nice exact values. So just be careful when you're doing your XYZ or you're doing your book work. If it says round to 1 decimal place, so forth and so on, then just do that. And they expect you to pull out your calculator to find these values. If it asks for exact values, then it will be a multiple of 30 or 45, and you should be able to identify those exactly. All right, let's go the other way. What if we have a rectangular and we want to go to polar coordinates? Well, given the point xy, well, r is equal to, don't forget, the square root of x squared plus y squared. And theta, well, we weren't given anything for theta, but let's just go back here for a second and look at the relationship between them. Let's go back here. All right, so if the tangent of theta equals y over x, then theta is equal to the inverse tangent of y over x. Now we have to be really careful because this only works if theta is in the 1st or 4th quadrant. So really, I'm going to put RA is going to be the reference angle. So we can only get the reference angle for the point, and then using common sense and our thought process, we can determine exactly what the coordinates are. So what do I mean by that? I'm going to put the reference angle is equal to the inverse tangent of y over x. All right, so now you just have to be really, really, really super careful here. You could do x over r equals the cosine, and that just gets a little bit trickier. So bear with me with this. Let's convert 3 square root of 2, negative 3 square root of 2 into polar coordinates. So 3 square root of 2, I don't know, let's just say it's about right here. Negative 3 square root of 2 is like right here. So they're going to meet right here at this point. So that's the point in rectangular coordinates. Now we're going to convert this into polar coordinates. So we're looking for two things. We're looking for this distance right here, and we're looking for this angle. I mean, we could use any angle. There's actually infinitely many answers to this. Again, be really careful because sometimes it asks you for a positive angle. So we'll give two values that would produce this point in the XY system. So first, let's do r. So r is equal to, because r squared is x squared plus y squared, r is going to be the square root of x squared, 3 square root of 2 squared, plus negative 3 square root of 2 squared. So my r value is going to be 2 times 9, right? So it's 18 plus 18 is 36, and the square root of 36 is 6, right? And then theta is going to be the inverse tangent of, all right, I'm going to put reference angle, the inverse tangent of, it's going to be y over x, so negative 3 square root of 2 over 3 square root of 2, which is the inverse tangent of 1, negative 1, right, which is negative pi over 4. So negative pi over 4 makes sense right here. So we can definitely use negative pi over 4. If we got negative pi over 4 and we were over in this quadrant, our point was 3 square root of 2, negative 3 square root of 2, 3 square root of 2, then we would know our reference angle was pi over 4, and we'd have to make a different choice. So therefore, we have what we need, and we can do our angle r theta can be written as 6 negative pi over 4. Okay, or we could have used any angle whose terminal side lands right there. So we could use this angle instead, which would have been 7 pi over 4. So 7 pi over 4, right? We could have used this side of it right here, and we could have done this, which is 3 pi over 4. But if I went 3 pi over 4, I'm no longer on the terminal side, so I have to go in the opposite direction. So then it would be negative 6, 3 pi over 4. And I can continue. There's infinitely many, different ways I can write the point 3 square root of 2, negative 3 square root of 2 in polar coordinates. All right, let's look at this guy. Let's convert negative 5, 12 into polar coordinates. So here's negative 5, here's 12. So here's an example right there. Right, so negative 5, 12, we're going to look at the length. The distance of this line is going to give me r right here. So r is going to equal the square root of negative 5 squared plus 12 squared, which is 25 plus 144, which is the square root of 169, which is 13. Well, that worked out nice. They don't always work out nice. Again, just follow the directions. If this didn't work out to a perfect square number under the radical, then you would either leave it in radical form or you would round it to however many decimal places you were indicated to do so. All right, now remember, we're looking for this angle. So we're looking for an angle that falls into the second coordinate. So the second quadrant. Oh my gosh, I'm apologizing. I'm very tired, but I gotta get through this. So push, we're so close. Let's see. So I'm going to use theta is equal to the inverse tangent of, it's y over x, right? So 12 over negative 5. But 12 over negative 5 is not a nice number. There's really no super awesome number that has tangent negative 12 over 5. So if I go into, let me see, what mode am I in? I'm going to go into degree mode. I like using degrees here. So if I do the inverse tangent, whoops, quit out of there. I'm going to do the inverse tangent of 12 divided by negative 5. Okay, and I'm going to get, it's going to give me approximately negative 67.4 degrees. So that's clearly not our angle of interest. So now you have to bring out your pre-calc skills here. So right here, this angle is negative 67.4 degrees, or approximately, but that's what we're gonna go with. So the angle that goes from the opposite side of the terminal side to the x-axis is 67.4 degrees. So thus in turn, by using the opposite angles, this is 67.4 degrees. So we can conclude that the angle that we need is 180 minus 67.4 degrees. In turn, we're going to call it 112.6 degrees. All right, so it's not exact. So therefore, I'm going to call theta my reference angle right here. So therefore, we're going to use theta equals 112.6 degrees. Don't forget your degree symbol. And the coordinates of my point are going to be 13, 112.6 degrees. Okay. All right. So now that we know how to plot points, let's talk a little bit about polar curves. All right, we're going to use these statements. We got to be careful here. Be careful with this one, just like when we were doing Cartesian to parametric. We have to be really super careful with our inverse trig functions, and we have to be really super careful when we're taking square roots of things squared. So we're going to use these things to convert equations from one coordinate to the other. So let's look at x squared plus y squared equals 16. Let's put this into polar form. Now, if you notice, this is just a circle of radius 4 centered at the origin, if you're familiar with that template. So how would this look in polar form? Well, x is equal to r cosine theta. So I'm going to replace x with r cosine theta. So we have r cosine theta squared plus r sine theta, right? All squared equals 16. Right now we can clean this up. This is not simplified. Watch how cool this is. This becomes r squared cosine squared of theta plus r squared sine squared of theta equals 16. Going to factor out the r squared. We get cosine squared of theta plus sine squared of theta. And what do you know about cosine squared plus sine squared? Well, this just equals 1. Right, so what we really have here now is r squared equals 16, or r equals 4. We could say r equals negative 4. It's going to give us the same exact picture. So this is saying this is all points. You can use any angle as long as r, the distance from the point to the origin, is 4. So if we look at our xy axis and we say 4 from the origin, 4 from the origin, so 1, 2, 3, 4, 3, 4, 1, 2, 3, 4, right? 1, 2, 3, 4. So, and then we went and we would do, this point was 4, this point was 4, this point was 4, this point was 4. Those would be all points 4 units from the origin. And it would give us the circle. So if I went 4 units from the origin, if I went negative 4 from the origin, it would just give me the other side. And theta can be anything. So r equals 4 is the polar equivalent of the circle x squared plus y squared equals 16. Let's look at y equals 1 over x and convert that into polar form. Well, y equals 1 over x. Y is equal to r cosine of theta. And that's 1 over r sine theta. Now, that can be sufficient. Now, this is where it gets a little bit tricky because there's lots of different things we can do with this. We often like to eliminate fractions. If we multiply both sides by r sine theta, you see that we get r squared sine theta cosine theta equals 1. So this is not incorrect. This is a little more visually pleasing because we eliminated the fraction. Even more interesting, what most books would do is they would say, keep in mind, we know what the sine of an angle times the cosine of an angle is. To the sine of an angle times the cosine of an angle, we can condense that into the sine of twice the angle. So if I just bring that 2 over to this side, we can rewrite the sine of theta cosine of theta as 1/2 the sine of 2 theta. So really what we have here is r squared times 1/2, I'll keep it in the same order, sine theta cosine theta equals 1. Now I want to get rid of the fractions again. I'm going to multiply by both sides by 2. We get r squared sine theta cosine theta equals 2. So this is not unacceptable. It's just not as visually pleasing as this. Oh my gosh, what did I just do? Nope. Oh my gosh. All right, bear with me. Sorry. Backpedal, I didn't do it. I need to make it through this lecture. Let's see. All right, let's go back here. So r squared sine theta cosine theta, we're replacing with 1/2 the sine of 2 theta. There we go. Much better, right? That's what we did. So we went from 2 trig functions to 1 trig function. So this is not incorrect, but if you see this instead of this, try to remember these identities. So we're going to multiply through by 2. We get r squared sine 2 theta equals 2. Now I'm going to show you something cool. We can graph y equals 1 over x in our calculator, right? So if we wanted to see that, I'm going to show you how this all works in here. So good time to do this, maybe, depending on I make it through it. Function. So if I go to y equals, I'm going to clear my other classes stuff out of there. If I go to y equals, and I do y equals 1 divided by x, right? We know what that looks like. It's 1 in each corner like that, right? Now, if you go back to mode, like you did previously for your parametric equations, now we go from function mode, we went to parametric last time. The third one over POL is polar coordinates. So let's do polar coordinates, ready? And let's do y equals, now it has r equals. So r is equal to, we have r squared. So, this is not a good example. Let's see. You know what? Let's go back up here. No, I can't do that one. I have to solve for r. I guess I could do it. Sorry, I picked a bad example. Let's go to the previous one. Yeah, let's just graph y equals 4. Right, let's go to this guy. Let's just do r equals 4. And then see what happens with the other one when we graph it. Ready? R equals 4. Boop, there's your circle of radius 4. Right? All right, let's go back. Let's see what I can do. See, and I started it. If we solved for r here, I could simply do r is equal to the square root of 2 over the sine of 2 theta. So let's see. I have a feeling I know what I'm going to do here, but let's see. We're going to go to y equals, and we're going to do the square root of 2 divided by the sine of 2 theta. All right, let's see what we get here. I got to parenthesis, I got to close it again. My guess, I'm only going to get 1/2 of it. Oh, no, I do get both halves. There we go. I get my little thing-a-doos. Right? So it did work. I wasn't sure if we'd need the plus minus, but I think if we did plus minus, we're going to get both pictures anyway, because this angle allows us to keep swinging around and get to those points on the other side. Right? Cool. All right, so we went from polar to Cartesian. Nope, we went from Cartesian to polar. This is going from polar to Cartesian. Let's turn r equals -8 cosine theta into Cartesian coordinates. Keeping in mind all our little tricks, we know that x is equal to r cosine of theta, y is equal to r sine of theta, r squared is x squared plus y squared are our basic ones. All right, well, notice here we have cosine of theta, all right? So wouldn't it be really nice if we had an r over here? Because then we could say r cosine theta and replace it with x. Well, we can do that. We can put an r over there simply by multiplying both sides by r. So isn't it true that r squared is equal to -8 r cosine theta? Many, 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 many ways to do this, but this is one of them. So now I know what r squared equals to. It's x squared plus y squared is my left side, and my right side is just -8x, because r cosine theta is just x. Now remember, cosine theta isn't x, r cosine theta is, so I had to introduce that r by multiplying both sides by r. So we can leave it like this, or, so this is perfectly an acceptable answer, or what I just want you to notice, what this is actually the graph of. I'm not sure if you recognize this as the graph of anything, but if I bring this 8 over to the left side, this 8x plus y squared, you may recognize this as something. If you think of your analytic geometry from your pre-calculus days, what I'm going to do is complete the square. So if you remember completing the square, we take half of this number and square it, which is 16, and add that to both sides. So isn't it true if x squared plus 8x plus y squared equals 0, then x squared plus 8x plus 16 plus y squared equals 16? I just added 16 here and here. Now, why I added 16 to both sides? Because x squared plus 8x plus 16 is just x plus 4 squared. So x plus 4 squared is just this mess, plus y squared equals 16. And you may recognize this. This is just a circle centered at -4, 0, and the radius is 4. So the equation r equals -8 cosine theta is just the circle x plus 4 squared minus plus y squared equals 16. And I know this one will pop up nicely. So let's graph this guy. Let's graph -8. Whoops, I'm going to clear it so I don't get the part of the other one in there. -8 cosine theta. Close my parenthesis. I'm going to graph it, and there we go. There's our circle of the radius. The center is -4, and the radius is 4. Now, keep in mind, most calculators are wider than they are tall, so that does look more like an oval or an ellipse, but it's not. It is a circle. These are tricky, and these definitely take practice. Often students just overlook the obvious when they're doing these, and they just take lots and lots and lots and lots of practice. All right, really super simple. Theta equals pi over 4. Convert that into Cartesian coordinates. Well, theta equals pi over 4. All right, what would we do here? Well, again, this comes with practice and seeing examples, so it's not a bad idea to watch some of the videos that XYZ provides for you, read in the book and look at the different general forms. One thing we can do is, I'm gonna do the tangent of both sides, one option. So if theta equals pi over 4, the tangent of theta equals the tangent of pi over 4, but the tangent of theta is y over x, and the tangent of pi over 4 is 1. So now multiply both sides by x, and we get y equals x. This is just the diagonal line through the origin. Theta equals pi over 4. Diagonal line, y equals x. That's it. Now, we could have done this, and I tried doing it with other trig functions, and let me just show you, it's just not nearly as pretty. If you use other trig functions, it does come out to be the same. So we could do, let's say theta equals pi over 4. We could do the cosine of theta equals the cosine of pi over 4. Now, the cosine of pi over 4 is square root of 2 over 2, so you can see why using the tangent would be more desirable here. But the cosine of theta is equal to, the cosine of theta, we have x is equal to r cosine theta, right? So x over r is a cosine of theta. So we can call this x over r, and the cosine of theta is the square root of 2 over 2. We don't want r, though. We just want it all in terms of x and y, but we know that r is equal to the square root of x squared plus y squared, and that equals the square root of 2 over 2. You might be saying, how can we ever get this from this? Well, let's just keep going. Let's eliminate the fractions. I'm going to cross multiply, and I get 2x is equal to the square root of 2 times the square root of x squared plus y squared. And then I'm going to square both sides. Right? So I get 4x squared is equal to, well, that's going to be 2, right? And we are going to have 2 times x squared plus y squared, right? So we get 4x squared equals 2x squared plus 2y squared, right? Subtract x squared, 2x squareds, we get 2x squared equals 2y squareds. We get x squared equals y squared. Now, when we take the square root of both things, both sides here, and you have to, again, be really super careful when you take the square root of things squared, x is either going to equal y, or x is going to equal the opposite of y. So how do we know which one it is? Well, theta equals pi over 4 is this right here, so that would be my answer. If this was 3 pi over 4 instead, our original problem, 3 pi over 4, we would get almost the same result in the end, but then we would be in this direction, and we would know it would be y equals negative x, or x equals negative y. So again, path of least resistance using the tangent, it just spit out the answer. Really nice for us. All right, some common polar graphs. Theta equals a number. When you have theta equals a number, it's just a line through the origin that makes an angle of A with the positive x-axis. So this is just going to be a line through the origin that makes, this is going to be A, angle A. Line through the origin. Which makes an angle of A with the positive x-axis. Right. And we saw earlier, theta equals pi over 4. Right, so theta equals pi over 4 would make a 45 degree. Right. Right, and this is the line y equals x. What if we had something other? What if I had theta equals 210 degrees? All right, what would that be? Well, it would be an angle through the origin, a line through the origin with angle 210 degrees. So 210 degrees is down here, so it's 30 degrees. Right. So that would be our line. What would this be the equation? Y equals what? What x? Right. So we have 210 degrees right here. So we would have, if theta equals 210 degrees, we have y over x equals the tangent of 210 degrees. Right? So y equals the tangent of 210 degrees x, and the tangent of 210 is, let's see, it's a multiple of 30 degrees. So it would be square root of 3, let me see, what is it? Sine over cosine, so it would be 1/2, it would be square root of 3 over 3. Let's see, negative square, no, positive square, no, positive square root of 3 over 3, hold on. Tangent of 210 degrees, so that's second square root of 3 divided by 3. Second square root of, no, push the right buttons. Divided by 3, yep, square root of 3 over 3. Over 3x, yep. Y equals the square root of 3 over 3x. Woohoo! So theta equals a number is always a line through the origin. Sorry, 210 degrees from there to there. There we go. All right, r cosine theta equals A. Anytime you have this, this is going to be a vertical line because r is just equal to x. Right. X equals A. So for example, r cosine theta equals 7. It's just the vertical line. X equals 7, and this is so simple and easy to put in your calculator. Go back into this. We're going to do, well, r, this is equivalent to, r is equal to 7 over the cosine of theta, right? So we're going to do 7 divided by the cosine of theta. We're going to graph that, and we see we just get the vertical line. Coolness. All right, this r sine theta equals a number is going to give us the horizontal line y equals b. Now remember, you can always look at it as r is equal to b over the sine of theta. Horizontal line, y equals b. So for example, if we had r sine theta, now remember your variables are r or theta when you're in the polar world. B would be my constant, let's just say -2. So this would be a horizontal line. Y equals -2. If we are to graph this, we would have to graph -2 over the sine of theta because its input's asking it in terms of r. So if we were to change this to r to be -2 divided by the sine of theta, all right, and we graphed it, there it is, horizontal line through -2. All right, r equals a. We did this earlier. R equals a is just simply a circle of radius a centered at the origin. See previous example. We got r equals 4, and I think it came from x squared plus y squared equals 16. If we have r equals 2a cosine theta, this, we actually did one of these. This is a circle. This is also a circle. Circle with radius. I should say radius absolute value of a, because when we talk about the radius of a circle, we always talk about the radius being positive. So this is going to be a circle with radius absolute value of a, even though there is the 2 there. And the center is going to be whatever the value of a is on the x-axis and 0 on the y-axis. So previous example again. We looked at r equals -8 just a couple minutes ago, cosine of theta. So in this case, a would be -4. So therefore it is a circle with radius. Remember, radius is always considered to be positive. Radius 4, centered at the actual value of a, which was -4 on the x-axis. If we have r equals 2b sine theta, now this is also a circle. It's a circle with radius b. Oops, I'm going to change that to the absolute value of b. And this one is centered on the y-axis. At 0b. So for example, let's suppose we had r equals -9 sine theta, right? So in this case, b would be -4.5. So this would be a circle with radius +4.5, centered at 0, -4.5. And let's just confirm that. Y equals -9. Nope, -9. Sine, let's clear that, of theta, right? And let's graph that. There you go. There's my circle centered at -4, 0. And if you count over, it goes -4.5, +4.5, +4.5, -4.5. Woohoo. All right, if you combine 3 and 2, we now get a circle centered anywhere. So this is going to be a circle with radius square root of a squared plus b squared, and it's going to be centered at a, b. So for example, let's suppose we have r equals 8 cosine theta minus 6 sine theta. Okay, so here a is 4, b is -3. So r is going to be the square root of 16 plus 9, which is 5, in the center, so therefore it's a circle with radius 5, centered at 4, -3. It's not bad to try converting these. So let's do that. Let's do y equals 8 cosine theta. 8 cosine theta minus, make sure you use your parentheses properly, sine theta. 6 sine minus sine 6 theta, and there we go. There's my circle, centered at 4, -3, and if you count, that radius will be 5. All right, the next ones, the cardioids and the limacons, are so super cool. There's just no way I can draw them by hand, so I figured this would be a great thing to read in your textbook in page 666, okay, and have fun with them, okay? So your to do for 10.3, your next to last to do, read 10.3, exercises. Well, the more you do, the better you'll get at them. 1 to 45. I say odd, every other odd, whatever works for you. Okay, and then you have your 10.3. Oh, no, it's not 10.3. I think it's 7.3. X, Y, Z. All right, kids, have fun with polar coordinates. One more section to go.